Extreme Fandom.
So here we have the 1974 free response AP. Let's take a look at question 2. We got the moment of inertia of a uniform solid sphere, mass m, radius r, about a diameter is 2 mr squared over 5. That language is a little odd to me. That is the moment of inertia is if it's rotated about its center. They said about a diameter. I don't know. It's weird language. I don't know. But anyways, that is the moment of inertia about its center. Its moment of inertia is 2/5 mr squared. All right. So that's moment of inertia about its center. The center of mass is placed on an incline. There we go. Right there. I placed it right there. And as shown and released from rest. All right. So I guess that's 0 and V0 equals 0. Determine the minimum coefficient of friction between the sphere and the plane with which the sphere will roll down without slipping. Oh, what's happening here? It's not slipping. Number one, there's a couple of conditions. The minimum coefficient of friction. All right. So that's telling me that this must be at static friction maximum, right? To find the minimum coefficient of friction, I'm going to need to, this needs to be rolling right at the ragged edge of slipping. So there are two conditions that need to be met in this problem. As long as they're met, we're good. But you need to recognize what they are. Number one, the friction. I'm going to draw the forces on this. We're going to need to sum some torques here. Let's see, it's rolling down the hill. So is that still on the screen? I hope so. I kind of went off the screen on the last one. Sorry about that, but I don't think anything important was cut off. We got the normal force perpendicular to the surface, and through the center we have the weight. Is that straight? I hope so. mg straight down, and we have, now here's the key, friction is acting right here, and it is F static maximum. That's incredibly important that it's maximum static friction. So if we're rotating about a center, we're going to use this, and we're going to rotate about the center. So therefore, the weight, the force vector is actually going through the point of rotation that we're summing the torques. So this can't apply a torque. Neither can the normal force because we're going to sum them around the center. I'm going to put a dot right on the center. Right there. There we go. We're going to sum the torques about the center. No torque, no torque. That is applying a torque, though. All right. So let's see what we got. We got the sum of the torques equal I alpha. All right. And we only have one torque. We have the torque due to friction, and that is going to be, it's going to be positive. It's going to tend to cause a angular acceleration in this direction. So we're going to go Fs max. That's got to be max. If it's just regular static, then we couldn't solve this. It's right at its ragged edge times r, I guess. Is that r? Yeah, r. All right. Is the radius of that thing. And then this is 2/5 mr squared times alpha. All right. All right, so we're going to use that the static friction max is mu static times the normal force times r, 2/5 mr squared theta. All right, so we can't solve this because we don't know the normal force and we don't know alpha. We're going to need more information. Well, we do know that Newton's second law also applies, so the sum of the forces equal mass times acceleration. Well, let's break that down into x and y. The acceleration is going to be along the x. I'm going to tilt the axis, right? I'm going to tilt the axis. I'm going to draw a free body diagram over here. Let's see. Let's tilt it like this. And we'll go Y, and we'll go X. There's our particle. And we got weight. And we got normal force. And we got friction static max. All right, and then here's our theta. All right, so if that's true, then the sum of the forces in the x, all of acceleration is going to be the x because I tilted my axis, max. So what do we got? We got Fs max minus mg sine of theta equals ma. All right, and then we also know that the sum of the forces in the y equals 0. It's not accelerating in this direction, so we got normal minus mg cosine of theta equals 0. So of course the normal force equals mg cosine of theta. All right, we got the normal force. That's a good thing. We need one other piece of information though. It's not slipping, right? So not only is that Fs max, but we need one more piece of information. Otherwise, we couldn't solve this because right now we have that. We don't have that. We don't have that. And we don't have that. All right. So we need to relate these two since it's not slipping. I'll write it down here. I'll use a different color. Green. I'm going to use green. We also have this idea that the acceleration, which in this case is going to be negative, equals alpha r. That's because no slipping. No slipping. There is no slipping. Right? There's no slipping, and it's a ragged edge of slipping. So there's no slipping, and it's at the ragged edge of slipping, so it's Fs max. So therefore, the friction static is mu s n. I could also say that this is... no, I don't think I'm going to do that. I think I'm going to erase this. I think what I'm going to do here is... I think I broke this into pieces too soon. Let me try this instead. This might be more efficient. I don't know. We'll find out. Let's find if this is more efficient. I'm going to solve this for alpha. I want my alphas to go away, so let's try this. Let's do this. Let's say Fs max minus mg sine of theta equals negative m alpha r, right? So I just substituted in negative alpha r for a, and therefore I can solve this. I can say Fs max minus mg sine of theta equals alpha m over r, and this whole thing is negative. All right. All right, so then we can substitute that into there, and we end up with Fs max r equals 2/5 mr squared times mg sine of theta minus Fs max all over m times r. Right? Right, just putting that in there. Substitute, boop. All right. Let's see, do our r's go away? Yeah, I think they do. We lose our r's. That's good. And looks like we lose an m too. All right. Beauty. All right, so let's see what we got. Fs max equals 2/5 mg sine of theta minus Fs max. That's Fs max. I know it doesn't look like it, but it is. Trust me. All right. So I'm just going to go... so this is Fs max. Bring this over here. Plus 2/5 Fs max equals 2/5 mg sine of theta. All right, we're getting close. I can tell. So what do we got? 7/5. So we got 7/5. I'm going to replace Fs max with mu static times the normal force equals 2/5 mg sine of theta. All right. Beauty. It looks like the 5s can go away. The normal force is mg cosine of theta. So we got mu s mg cosine of theta equals 7. Sorry. 7 mu s mg cosine of theta equals 2 mg sine of theta. Why am I carrying those mg's around? We don't need to do that. That's completely unnecessary. All right. So it doesn't matter what planet you're on, and it doesn't matter what the mass of the solid sphere is. Interesting. All right. So it looks like we got mu s equals 2/7. We got sine over cosine, which is tangent. It's tangent. Mu s equals 2/7. Tangent theta. There is our, that's our static friction. There we go. It gotta be at least that. At least that. Otherwise it's gonna start sliding, slipping, sliding. If it's less than that, it's gonna slip and slide. If mu were 0, would the speed of the sphere at the bottom be greater, smaller, or the same as in part A? Well, guess what wouldn't happen if mu was 0, right? There would be no torque on this thing. There would be no torque, so therefore it wouldn't be rotating. In either case, they lose the same amount of gravitational potential energy, so this much gravitational potential energy becomes kinetic energy. But if mu is 0, then it's not rotating, so all the energy is in translation. So this is what you want to say. You want to say that in both cases, number 1, they gain the same total kinetic energy. All right? So they gain the same total kinetic energy whether mu is 0 or not. Let's see. When mu equals 0, all energy is translational. When mu is 0, all energy is translational because it's not rotating. Therefore, when mu equals 0, V1 is greater. All right. So the velocity at the bottom is greater if there is no if the coefficient of friction is 0, because all the energy is in translation. All right, but that's what we want to do. You want to say they both gain the same total kinetic energy. When mu is 0, all the energy is translational. Therefore, it is translating faster when the coefficient of friction is 0 and there's no friction. All right, that's 1974, number 2. I hope that went okay. And we will talk soon, I'm sure.
Extreme physics.